So I will talk about structural integrity analysis of a Kaplan turbine cover. You can see the authors. You can see now the turbine. This is vertical turbine made by Russians and built in a large hydropower plant, Miodrag. But half of it is in Serbia, the other half in Romania. That was a large international project, bilateral. And you can notice that it is 40 years old. You can see it down here. It's now even more, probably 50 years old. This analysis is about 10 years old, by the way. And at that time, 10 years ago, revitalization and modernization of turbine aggregate 8.4 was performed. And during that period, we also had a chance to experimentally investigate the current state cover. And turbine cover you can see here in the cross section. That is some component made of structural steel, classical structural steel. According to Russian standards, ST3, it's about ST 335 or maybe even less. We'll see it later. So quite a common structural steel. A critical component in that cover is shown here. It's segment, as you can see it as a sketch. For one is the one that had the most of defects, which I will show soon. And here you can see how it really looked like. So in this introduction, let me also say that in the scope of this investigation, once this cover was to be replaced, we could apply different non-destructive methods to find defects, and also we could test some destructive testing to get mechanical properties, including fracture mechanics properties, parameters or properties, which we explain today with the aim to assess structural integrity. So magnetic particles and ultrasound testing is presented here briefly. Also, a few words will be devoted to chemical composition, tensile properties, well, impact toughness, no, not today. Fatigue crack, also not today, but just classical linear elastic fracture mechanics. In addition, some numerical analysis was also performed, classical linear elastic stress strain, so that we know stress level in critical regions, so that we can calculate crack length and compare it with the critical crack length. You will see that later on. Here is the sketch of the segment. You can see in red some indications, and also in red you can see locations. So this is ultrasound, this is the front view. Now here is the back view with also some indications, some defects, lack of penetration, most of them. Now for magnetic testing also, locations and indications, and once again, and finally in this cross section as well. So it was very thorough investigation, non-destructive testing, and you can see how it looked like in reality. This is just one defect detected by ultrasound. So finally, to summarize it, few most important defects that were found were lack of penetration. You can see it here. That goes that went up to 25 millimeters, and a few lamellar tearings that went up to 10 millimeters. So those were still, those were unacceptable defects. Many others were acceptable, but what we knew is that this component actually survived, because we just took it out of the turbine itself. Anyhow, of course, with these findings, we decided to replace it and also to investigate it to get at least tensile properties. You can see it here briefly in different direction. It's important to emphasize that direction which we marked as Z, as you can see here, which is perpendicular. This is what you practically can see is the front of this sample that we took out to make specimens, and doesn't really matter. One of the directions was critical, doesn't really matter which one. At this point, you can see very, very low ductility or in that contraction, actually, in that direction. The other directions are quite okay. You can see them here. Yield strength, tensile strength, elongation, contraction, but here in this direction, it's obviously quite a brittle material. So it was really important to make this analysis. This is a finite element analysis with regular regime. So loading is sketched to the left, and to the right you can see isostress lines, and pay attention about number 3 here, line number 3, which is 45 megapascals. And here is the location of these unacceptable defects, as I mentioned, lamellar tearing and lack of penetration. The other regime, which is irregular, differs from the previous one because loading is different. You can see it here to the left. Forces here are now missing, but that is less favorable for the stress state. So now in this critical region is number 4, isostress line number 4, which is about 70 megapascals. So very simple calculation about critical crack lengths, which is based which was done once for the edge crack, simple edge crack in 2D in a cross section, sorry, and in the other case for the surface crack inside 3D is internal crack. So we found out that critical crack length is 354 for the regular regime and 146 millimeters for the irregular one. That was the case for the edge crack. And of course, more favorable situation for internal 3D crack is shown here. So the most critical is edge crack. Of course, it is conservative assessment. It is valid for irregular regime, and it is still 146 millimeters. If you remember, those unacceptable error defects were up to 25 millimeters. So from that point of view, we can conclude, as written here, that both lack of penetration with maximum 25 millimeters of length and lamellar tearing in the base metal with maximum 10 millimeters are much shorter than a critical crack length. So we could explain why this cover survived 40 years. In some other presentations, in other conferences, we will present also fatigue crack growth analysis, but for today, I think we had enough. Thank you. And we are
Thank
late.
you very much for this nice presentation. Very practical issue. I think it is important to show such problems during the conference. We have a time for a very short question, please. Do we have any question? Yes, please, Professor.
Good morning, Professor Sedmak.
Good morning, Professor Tavares.
So, well, 40 years is a long period.
Yes.
So you mentioned you had a finite element modeling for the cover. Do you have an idea? Did you do some model analysis on this? Do you have an idea why the locations were those that you showed the defect locations?
Most probably because of welding itself, not because of component geometry or nothing else, but simply they didn't make it according to standards. But as we could see, even that can survive.
Yeah, true. Thank you.
This is good with welded structures and joints. They can be with large defects and still they can survive.
Thank you.
You're welcome.
Well, thank you very much for all the participants within this session. We are ending this session. Thank you. Thank you for great organization, to organizers, to
Indeed.
For such a nice event that we have a possibility to meet all together and to discuss such nice problems. So I think we have only 4 minutes to the next session. We can make a very short break and start the next session on time.
Espresso.
Yes.
For coffee.
Thank you all. Okay, see you in the next session.
See you in the next session.
See you.
Thank you, Andre.